But I'm sure Niall, who I almost dislike everything about him because he's like, it's that moment we realise the speaker is 30 years younger than me, roughly. But this is one of the great things about NI-DevConf, bringing people together of all experience levels. Niall's going to talk to us about serverless and how it's really just someone else's computer. Niall, please welcome Niall to the stage.
Thank you. Yep. Back in 2022, our technology strategy at Instill recognized the huge benefits of serverless and that we don't need to plan for capacity, patch servers for newly discovered vulnerabilities, and are able to scale resources right down to zero when they aren't in use, while also being able to scale them right back up again in seconds. After reflecting on these benefits, there was only one clear conclusion we could come to. And that was that we want to embrace serverless on our projects. However, we also recognized that was going to require a huge cultural change in how we approach building software. Serverless is different, there's no doubt about that. How we test it is different, how we deploy is different, and sometimes you have to come to terms with the fact that writing less code is better. But as a company, we've absolutely done this. We've deployed several serverless first workloads in production, but now that we're a few years on, I believe there's a next step in that pathway. And that's the importance of deploying serverless workloads that are maintainable. And that's what I want to talk about today. As you probably already guessed, this talk is going to be a deep dive into using serverless. If not, to be honest, you're probably in the wrong talk. And I'm going to do this by presenting 6 things that I've come to realize are crucial for supporting and maintaining serverless applications. However, first, I want to address the question that I know is in all of your minds. What does it mean maintaining serverless applications? Surely serverless just takes care of all that for you. Well, yes, you're correct, and as our technology strategy here at Instill pointed out, with serverless, we're not worried about infrastructure management around security patches or capacity, but there's still some aspects of maintenance that I think are often overlooked because, sure, serverless just does all that. I'm Niall Keys, apprentice software engineer at Instill, current AWS Cloud Club captain for Belfast, and I'm recently added AWS certified to that list by achieving the new AI practitioner cert. But we're not here to talk about AI today. The project I'm going to talk about today is Stroll, a serverless first car insurance platform built in AWS. The NIDC regulars in the room might remember Matthew Wilson, one of my colleagues, sharing about this project's development story previously. But if not, don't worry, as there's hopefully still a lot of value that you can get out of this talk in isolation. Saying that, the insights from this journey have been shared on our website, so I'd really recommend reading those, as there's lots to glean from them, especially if you're still in those early stages of your serverless journey. I've also included these links in the resources that I'll share at the end of this talk, so don't worry if you're not able to grab them now. This project has since reached feature complete and is scaled up to cover all of the UK. But has our architecture lasted for this? Well, we've completely ditched serverless. No, only joking. Don't worry, that's never going to happen. But that's because in maintenance mode, serverless still continues to deliver the benefits that we know and love, such as ease of disaster recovery and security updates. To demonstrate this, I'm going to tell you about a time that might cause some of the Linux fans in the room to shiver. CVE 2024-3904 is a vulnerability that was discovered last year in Linux distributions, which opened up an SSH backdoor, like my colleague Michelle was chatting about in her talk this morning, granting bad actors the ability to enter the system. Here at Instill, we obviously had clients running on a range of different systems, and when discussing our strategy around this over on Slack, I think my colleague summarized this perfectly. One of the main benefits of serverless is that you don't need to worry about patching for newly discovered vulnerabilities. And that's because the cloud provider, in our case, AWS, manages that for you by patching the runtime and releasing a new update, which your resource will automatically use. This is obviously one of the huge benefits that we talked about back in 2022 in our technology strategy. However, serverless developers don't switch off just yet, because there's something that if we scroll down in the documentation where the quote on the last slide was taken from, we see this, and that's the AWS Lambda runtime version deprecation policy. Lambda deprecate a runtime when the upstream language maintainers mark their language end of life or security updates are no longer available. When a runtime has been deprecated, you'll no longer be able to update your Lambda code, and as a result, you'll be blocked from deploying updates until you do so. And that brings me on to my second lesson. And that's the importance that you carefully plan for runtime updates. This isn't something that's managed for you, and therefore, as someone who's maintaining a serverless application, you must keep track of when your specific runtime is reaching end of life. But once again, you likely have another question on your mind. What's the big deal? I just go to my infrastructure as a code framework, such as CDK, which we use on Stroll, and bump the runtime for each of the Lambda resources you're using. But this is where things can get a little bit tricky, as each runtime comes with a specific version of the AWS SDK. So if you want to avoid bundling the necessary packages in your Lambda deployment, you're going to need to upgrade this in parallel. However, I do know there's mixed opinions around this, but I think that we can all agree that at the very least, not bundling is going to have an effect on your cold start, which we'll talk about a little bit later on. Even if you're certain that you want to bundle the SDK within your Lambda, it's still a good idea to keep this SDK upgrade in mind, because similarly to the runtime, the SDK has a maintenance policy. After the SDK version that you're using enters maintenance mode, releases will only include critical bug fixes and security updates. A maintained version of the SDK will not receive API updates for new or existing services, or be updated if any support is added to a new region, for example. With end of support, all the updates will cease, including those security fixes, so it's extremely poor practice to stay on those updates at this point. However, these upgrades aren't as simple as just bumping the version like we saw in the last runtime upgrade, as they often have breaking changes that can be extremely painful. We felt this on the Stroll team during the V2 to V3 migration, which I know if anyone else is working on serverless in the last couple of years probably went through the same thing. One of the changes was around instead of the entire SDK, you had to import the individual services or commands that you were using. Thankfully, we were doing this beforehand because we wanted to keep our Lambda cold start as small as possible. However, one way that we were affected was around how promises were handled. Before, in V2, promises were handled by you, whereas in V3, this switched to be handled by default. This was a great change, and AWS released tools to enable you to do this. However, it only took you part of the way, and it was still quite a manual process to get all of the code updated. And this was especially true when you add the nature of the application being serverless on top of that. Due to its very nature, what serverless is, you're making more AWS SDK calls to different managed services within Lambda. And you can imagine when you scale up the number of API calls made in the serverless system, this SDK upgrade can become quite a substantial update. For this reason, you're going to want to bookmark your own runtime distribution deprecation policy, along with the relevant SDK maintenance policy. Both of these I've included in the resources link that I'm going to share at the end, because they're essential that you use these day by day. Whether or not these two updates are dependent on each other will depend on whether or not you're using a runtime or a bundled version of the SDK. But nevertheless, you're going to want to make sure you have the appropriate time to address both updates in your application timeline. Additionally, you're going to need to bookmark the service quotas. When building an application, especially in the early stages, considering your AWS service quotas are crucial to avoid hitting limits later on. But firstly, what is an AWS service quota? Well, AWS define these as the maximum values for resources, actions, and items in your AWS account. Just a few days ago, as part of the announcements in the lead up to reInvent, which I've been closely following, AWS updated one of the service quotas by announcing an increase in the number of S3 buckets which can be deployed in a single account. And this is, however, just one of the many different quotas there are for each of the services. Each of these service quotas are outlined in the documentation on screen now, and every one of you who are working on service applications should have these bookmarked when designing applications. And to demonstrate the importance of this, I'm going to tell you about another story from the Stroll project. There we were, needing to deploy an application that would run a workflow of tasks using data stored in DynamoDB on a regular schedule. To all of us, this sounds like a textbook example for a step function trigger by an event bridge rule, doesn't it? And that's exactly what we've done. In this process, we consider a 60-day window to issue renewal invites, where we fetch the renewed policy from DynamoDB and filter these one by one based on the insurers that have offered a renewal offer for that particular customer, and then process them one by one using a map and a single step function. This was all well deployed in production until one morning. I wake up, check New Relic, and see there's been a spam of errors throughout the night. Quickly open the AWS console to be met with the horror that every step function has failed since midnight. At this point, I was in panic stations. Did I deploy something that wasn't right? Have we changed anything? What's going on? But I needed to take a deep breath and perform root cause analysis. This problem initially didn't make a lot of sense because the process or workflow itself had failed, but none of the steps within the workflow had failed or thrown any errors. However, when I glanced at the top of my screen, I saw this error. This had happened because the 60-day window we had now entered at midnight had a lot more policies coming back from DynamoDB, meaning that the state being passed down from the first DynamoDB request was exceeding a quota set by AWS. At this point, stage 2 began, which was to determine what on earth the quota was that was causing me this pain and was causing these executions to fail. And that was the task state size quota put in place to limit event input and output passed between the states in a step function to be equal or below 256 kilobytes. With the problem now defined in root cause analysis, I had to determine a solution to what that problem was. Initially, this quota seemed quite limited, and I felt the obvious fix was to go into the AWS console and request a quota increase. However, as you can see when I go and try and do this, it isn't possible, as it's a hard quota tied to the underlying encoded string used in this context. This meant it was back to the drawing board, but after digging through the AWS documentation, it became clear that the solution was to update the step function configuration to use what was called a distributed map in the place of a standard map, which we were using currently. With this change, we were using the step function itself to handle batching the event metadata for the payload into the map stage, therefore ensuring that the quota is never exceeded. It does this by splitting the map into as many separate executions as necessary, and therefore you're letting AWS manage that you never exceed that quota. The change itself, as you can see, was pretty simple, again demonstrating the power of step functions. As I was able to just add in the distributed map config and deploy, executions were successful and customers were receiving their renewal invites again. However, it's now etched in my brain to consider the long-term load when developing an application and ensuring any quotas on that particular on the services that you're using. There are more quotas just like the step function state that are much smaller than you expect. Some of these are at a resource level, such as the maximum duration of a Lambda execution, meaning that you should definitely consider a different solution, such as AWS Fargate for long-running tasks. And again, from Lambda is the concurrent scaling rate, where you're only actually able to have 1,000 executions happening concurrently. This is surprisingly low, especially if you think about how applications scale to traffic and things like that. While there's others that are at more of an account level, like the limit on IAM rules, enforcing the importance of developers having separate accounts for testing. So hopefully just this has whet your senses slightly for the types of service quotas you need to watch out for, and I'll see people panic searching for their own resources for the duration of this talk. However, don't fear, because I've included this also in the links that I'll share at the end for people to dig into in their own time. One of the things that made this process really easy was working out what was going wrong, and to work out what was going wrong and pick that up quickly was because of the observability that we had in place and ease of debugging for customer journeys. I'm looking forward to John sharing about this later on, but it's no surprise that for serverless, it's just as important that we can easily identify a customer's journey to see what the cause of the issue is, especially when that issue is in production, like we just talked about. The use of serverless, though, as you all probably know, makes this slightly more complicated. Because of the distributed systems, there's some services AWS provide, however, that can make this process much easier. And the first of these is what we just saw. I'm a big fan, AWS Step Functions. They're a visual orchestration workflow service provided by AWS that make it really easy to see what's happening within an orchestration of events in a workflow. We use this anywhere where orchestration is important on Stroll, such as the midterm adjustment process shown on screen now, which at a high level allows for changes to be made to a policy version stored in DynamoDB, and the customer is notified through SES. There's some other things happening, like document generation. Now, when I first saw this workflow, I was probably like a lot of you and thought I was never going to have any notion what on earth was going on. But due to how clearly this state's laid out, it made it really easy to understand the business logic and different rules that were going on. However, I realized that the insurance domain is much too complex to understand in the duration of this talk, so I've deployed a much simpler example to demonstrate the possibilities here. In this process, we send an email via SES, call out to a Lambda to do some processing on a payload, and record those results in a DynamoDB table. Much simpler than the previous example. So when I go ahead and run that, we see how it looks when all the steps are successful with the state clearly marked out. However, if something goes wrong, like for example what's happening now, for example within the Lambda when it gets to that stage, you see that if we select that state, the error and stack trace are shown on the left, making it easy to identify where the error has occurred, debug the issue, and quickly implement a fix. Once this fix is implemented, we need to think about how we can rerun the failure, because obviously we need to complete the rest of the steps for that customer to be successfully processed. And in this case, as I just said, we've already notified the customer via SES, so we're not going to want to resend the entire workflow. We're not going to want to rerun the entire workflow. So instead, we're going to use one of the more recent features brought to step functions, where you can redrive from a failure. By redriving, it means that we'll rerun the step that didn't succeed. We'll not rerun the step that succeeded and subsequently sent an email to the customer, but instead we just restart the execution where the failure has occurred, and if successful, proceed with the rest of the workflow, which, as you can see, has happened here. There's only one step left after the failure, but the whole workflow has now been successfully completed. All in all, I must say, using step functions makes tasks much easier to debug what and where something went wrong than it is if we do this all in Lambda. There's some features in our application that were developed before step functions, and therefore orchestration is still happening within a Lambda because we haven't migrated them yet. However, when debugging a failure, these features are much harder to work out to locate errors in, as you miss out on that state map that we talked about being provided from step functions. AWS X-Ray is the other service that takes this one step further by providing the same level of observability for your application as step functions does, but giving you end-to-end visibility of your entire system using what's known as traces. These traces allow you to view a trace map of your resources that have been called in that user action, such as here where a client uses a certain part of the web app that triggers a GraphQL query resolved using AppSync with both direct integrations with DynamoDB, but also calling out to a Lambda function, S3, and even triggering another external API. Each of these user flows has an ID associated with them with any logs that are written to CloudWatch during the flow, which are also consolidated and can be viewed at the same part of the console as the map can be. As the user experience of the Stroll platform, though, was going to be mobile and with a web app, we had to consider a third-party service for client-side login, and we wanted to make sure that we could have all the logs in one place so that if I was logging in on a support day, you were able to see exactly what went wrong all in one place while then digging into the console if and when you need. On Stroll, for this we use New Relic, which I know is widely used. And as the AWS X-Ray Trace ID is included in what we push to CloudWatch, and therefore onto New Relic, we can also query using Trace ID in exactly the same way as we did in the console. X-Ray can also identify parts of the user requests that are causing the most latency. A lot of this latency, as you can see, is unsurprisingly coming from when we're talking to third parties through their APIs. However, as you can see, the GraphQL Lambda here has more latency than the other Lambdas around it. This makes sense, though, as we send requests to third parties that we provide over AppSync here. However, it's important that we can address this latency if it's at all in our control, as how fast the application loads is critical, as even the smallest bit of unnecessary latency can cause your user frustration. If our Lambdas are the source of this latency in production, we must do all we can to ensure they're at their most efficient. But as anyone who's familiar with Lambda knows, cold starts hinder this greatly. Lambda have an execution lifecycle, and the init phase is referred to the time taken to start up an environment, where when Lambda is first executed, the cold start is referred to the time taken to run this init phase. However, there are a few things that we can do to try and reduce this, and the first of these is to consider an alternative runtime. The AWS low latency runtime was recently released for JavaScript, which is much more lightweight and therefore is less of an environment to set up during the init phase. However, there's also AWS Lambda Snap Start, which has been around for a while for Java, but actually just this week, again in the lead up to reInvent, support has been announced for Python and .NET runtimes, where the init phase occurs on deployment instead of when it's called. When it occurs in deployment, the environment is then cached for reuse. So when the function is called, we pull up this cache, and the cold start is completely eliminated. However, sometimes that's much more complex than what you need to do, and simply reducing the dependencies bundle in the package is enough. This could be by only importing the packages used, or by utilizing the built-in version of the AWS SDK instead of bundling your own, as we talked about earlier. On the other hand, sometimes the most efficient decision to reduce latency in a Lambda is to increase the memory. You might naturally assume that this is going to cost more. However, as shown in the example on screen, if a Lambda function with more memory runs faster, it will actually cost less, because while the cost per millisecond is higher, the reduced execution time leads to a saving compared to a lower memory Lambda that runs for longer. Determining this optimal configuration can be complex. But we can use the AWS Lambda power tuning tool to help automate this. This tool works by testing several different configurations using step functions before generating some graphs that highlight the best memory configuration for the Lambda being tested. We can ensure that our Lambdas are running at the most efficient memory by setting up some observability around cost. This way we'll be alerted when a Lambda starts to cost more than the expected amount. This type of monitoring is what we refer to as resource level cost monitoring, which, as you can imagine, is when costs related to an individual resource like Lambda, such as Lambda in our example. For this, we use AWS CloudWatch alarms. However, we can't explicitly get a cost of a single Lambda execution in CloudWatch. However, based on what we've just seen with Lambda duration, that's a good symptom of the cost. Therefore, we can set up an expected duration, which obviously will differ per Lambda, so we'll need to be some testing during development. We set that expected duration when configuring the alarm, and then we'll then send an email or a message on a third-party service like Slack using AWS chatbot when that alarm is exceeded and the threshold is exceeded and the alarm is activated. At this point, we who are maintaining the application can go in and use the tools we've just looked at to work out how we can reduce this cost-causing latency. Account level monitoring then is also important. As we talked about the concept of individual developer accounts for testing, we can set up zero spend budgets using AWS budgets, which means as soon as infrastructure begins to cost money, the developer which is associated with that account, along with some admins if necessary, are notified. After the zero spend budget is exceeded, we can also tier the budget so the developer is notified at each stage of the budget being exceeded. This type of observability is key for us to take on that frugal architect and ensure that our serverless application cost doesn't scale hugely when our load increases. Thanks for coming along to my whistle-stop tour of just a few things that I've found helpful when maintaining with serverless. As I mentioned, any of the resources that I've talked about during the talk, whether or not that's been different policies, such as the runtime policy or the SDK maintenance policy, or that QR code, or if you don't want to look at the QR code, if you go to learn.instill.co/NIDC/supporting-serverless, it's all there. Obviously, the benefits of serverless are still very much there. There are things that we must do, such as managing the runtime, considering service quotas up front, and having the proper observability in place that will enable you to have your serverless application run smoothly for the years and decades to come. Thank you.